I think we'll go ahead and get started. So our first talk today is from Mairi, and she's going to be talking about the unweaving of the fabric of the universe. And I think this is kind of a big picture look at different theories of quantum gravity and their relationship to cosmology. And I'll tell you when you got about 45 minutes if you'd like.
Well, good morning to everybody, and let me start by thanking the organizers for this invitation. Okay, so good morning again, and let me start by thanking the organizers. I've never been here. It's a pleasure to be here. It's a pleasure to be among some physicists and particularly many philosophers. So the talk which I'm going to give is actually addressed not to physicists but to philosophers, and I would like to raise some questions from the point of view of cosmology, and hopefully this can somehow initiate some kind of discussion. So, the title of the talk, Unweaving the Fabric of the Universe, some of you might wonder actually, whether this is a purely philosophical kind of question or not. And what I will try to highlight, that actually something that lies between theoretical physics and mathematics, using data that we have either from astrophysics or from high energy physics, and trying to test the various theories. So, let me start, the plot. So one might indeed start wondering how space and time has emerged, how the space and time somehow they can create this four-dimensional space-time in which the evolution of the universe takes place. And in order to address this question, you have to combine mathematics and physics. And at the end of this discussion, I will raise the question whether the fact that we have not found so far a successful kind of theory of quantum gravity, we have proposals but not a theory, might lie in the fact that probably we might not have the correct mathematics. So indeed, the dream that Einstein had is to be able to unify all the subatomic forces with gravity in a way to be able to have one theory where the whole kind of aspects of the nature could take place. And that was the dream of Einstein, which has not been realized and became the dream of various generations, subsequently of theoretical physicists. And the point is that quantum mechanics could not fit with his theory. So everybody knows what is general relativity, the description of the warps of space and time. And the last prediction of Einstein's theory has been confirmed with the direct detection of gravitational waves on the 14th September of 2015, and by now we have of the order of 30, 40 kind of events, which hopefully soon we're going to make them public. Now, general relativity is a very successful theory in order to describe the whole evolution of the universe, how galaxies, clusters of galaxies and so on, they evolve. However, when you're going to zoom in subatomic scales, then the whole picture is going to change. Certainties become probabilities, and now we have somehow to enter the world of quantum mechanics. So quantum gravity is the theory which is going to give you the vocabulary to being able to join the curvature of space-time with the probabilities of events. And like that, we are going to put together the macrocosm, which is smooth, with the microcosm, which is very lumpy. Now, of course, you might wonder, when do we need such a theory? Of course, we don't need it in our everyday life. We can happily live without such a kind of theory. But there are two cases where, indeed, we need to put quantum mechanics and gravity together. That is when you're going to study the center of black holes, which you all know. The stars, when they use all the kind of nuclear fuel they have, they just have a supernova explosion. What remains, if they're heavy enough, it is a black hole. And also when you take Einstein theory, and you take the equations and you're going to evolve them backwards in time, it appears a point where you have ultra high curvature, and then you have very extreme kind of conditions. This is what we call the Big Bang, which took place something like 13.8 billion years ago, and then the theory cannot handle such a kind of situation. So the question is how you can come with a theory which can describe such extreme conditions. So one might therefore kind of attempt to ask the questions: how did the universe came into being? What was before the Big Bang? Okay? So space-time has kind of invisible structure which determines the way we're going to move, in the same way that the skier goes toward in the slope, and the bumps are going to define his motion. And this kind of structure is what we see as the force of gravity. Now there are many different, there are many different theories, proposals as I call them, of quantum gravity. But let me first start with how one was going to try to do quantum gravity. So there are two questions that you can ask. How quantum effects are going, quantum mechanics are going to affect gravity, and how gravity are going to affect quantum mechanics. And there are two approaches that one can use. Either you quantize gravity, or you gravitize quantum mechanics. And usually what we do is we quantize gravity. So basically what we need to do is to give up the kind, the music doesn't come from me, it comes from somewhere. So actually it could have some music, but I don't know. So we have to somehow to need to give up something which in the limit of GR is valid and something in the limit of quantum mechanics is valid, but beyond this kind of limits, these theories are not valid. So, the plot thickness. So, the theories, as I call them, means proposals of quantum gravity in an alphabetical order, is ADS-CFT, asymptotically safe gravity, causal sets, dynamical triangulations, group field theory, loop quantum gravity in spin forms, metric sensor models, non-commutative geometry, string theory, and so on and so forth. So, how can you test such theories? Okay? So what we try to do, and here is a big jump, which I will comment on that later. What we try to do is we try to compare predictions of these theories with the data which we have. And now this has two positive aspects. On one hand, we can now work with the cosmological model, I'm a cosmologist myself, which is inspired from a fundamental theory, which is good. And on the other hand, this kind of framework is going to give us probably the unique testing bed for such kind of theories. So now I would like to take you in a very quick tour in cosmology, because I want to criticize a couple of things which I will then probably we could discuss. So as you know, the model that everybody uses is what is called the lambda CDM model. This is a model which comes from the classical theory of general relativity, solved in a particular kind of background, homogeneous isotropic universe, the FLRW universe. People yesterday put some question, I don't use any questions today. And with a positive cosmological constant and a cold dark matter ingredient. Why you do that? Because you want to fit the data that tells that today the universe is in accelerated expansion, and it tells that you need some kind of cold dark matter in order to fit the kind of flat rotation curves which we have. And of course, if you take this framework, then you can explain within this framework the cosmic microwave background temperature and isotopes which have been detected. Now, in this model, we have about 67% of dark energy, and we have 29% about cold dark matter. And therefore, you can wonder, is this model consistent? Is it motivated? Is it proven? Is it unique? In addition to that, as yesterday there had been discussion, you put a kind of early era of accelerated expansion, which is called inflation. Now, I believe that yesterday in the talks we heard, inflation has been associated, the notion of inflation, with a scalar field. I would prefer to be a bit more general. For inflation is an early era of accelerated expansion. We don't know where it comes from. Now, if you take that as a starting point, then inflation, this early year of accelerated expansion, if it was given in the standard way that we have through an Newtonian field, then you have that quantum fluctuations could generate the initial kind of roots that give the structure in the universe and the cosmic microwave background. Now here I would like to make a comment. What has been shown so far, Einstein's perturbed equations are unique and can be solved in a unique way, provided you give initial conditions. The initial conditions that have been in agreement with the data are what we call adiabatic initial conditions. An example is inflation, is not unique. Okay? So that's in order to make a kind of comment when we say, we have shown a kind of consistency with a diabatic initial condition, example, inflation. Now, and of course, as we heard yesterday, there are open questions. The onset of inflation. How probable is to start with the initial conditions? So, because the majority, the bulk of the work, there are exceptions, but the bulk of the work has been studied within an FLRW universe. So you start with what you would like to solve. What is the nature of the phantom field? What is the compatibility you are going to have with high energy physics models? And there is a problem. I personally believe that given that the energy scale at which inflation should have taken place, it's a quantum gravity effect, so what we know is the mechanism of inflation, which it's much easier to do it through a scalar field, but I don't believe that it's a scalar field that drove the inflation. But that's another story for me to discuss. So, the lambda CDM model is a phenomenological model. So, by construction, it is working. We built it so that it works. We put two major ingredients so they are consistent with the data. We don't know what is the dark matter. We don't know which dark energy and inflation, despite thousands really, not to say, I don't know, even more, of papers, it remains a paradigm in search of a theory. So if I go back to the questions I raised at the beginning, is the lambda CDM consistent? Of course it is. It was tailored to be as such. Is it motivated? No. Is it proven? No. It is unique? Well, no. So these are some kind of questions that we have to keep in mind. The fact that we do not have something better, this doesn't mean that this is the only kind of explanation we should have. So, and here is the comment that I would like to make. So, what we do is the following. When you take the data, raw data, out of nowhere, you can do nothing with them. So you have to analyze them, and to analyze them, you put them within a particular framework. The framework, you have built it with the knowledge you have about local space and local time, and you extrapolate that. To my mind, the laws of physics depends on the scales on which you are. So now what we are doing is, therefore, we built this model, we analyzed the data within this model, and of course we found consistency. It's a consistency check. So that is something that we often forget. So I think it's good with meetings like that, because we might start wondering the assumptions that we make in our daily kind of work. So the plot unfolds. So now I would like to take three of the models that I said before, and just give you a highlight of what they are, and then what you can get out of them. So I've been working with many of those. I'm not going to tell you what's my preference, probably none. Yesterday, Daniele talked about group field theory, group field cosmology, so I'm not going to touch upon that. I'm going to briefly talk a few things about string theory. I'm going to say a couple of things for loop quantum cosmology, because there all of these non-perturbative approaches to quantum gravity could be embedded, let's say, so a paradigm. And then I will spend a bit more time on the non-commutative geometry approach, because I think it's the only one that has not been covered so far. So, string theory. So as you know, here in this approach, matter consists of one-dimensional objects. So when you see them from far away, they look like points. There are two types of these objects. They can be closed things, like the graviton, or they can be open ones, like the photon. Now you have that all particles can be shown like being different kinds of vibrations of such a string, and then you have intercommutations, splitting of these things that can represent the various interactions which you might have. Now, this is an example of quantum field theory. Okay? In quantum field theory, you combine the postulates of quantum mechanics and some additional axioms which you put. For instance, space-time is continuous, which means that locally it can be approximated by Minkowski space-time. Measurements can in principle be made on arbitrary small length scales. The results of these measurements satisfy locality and causality, which means that all the matter and the forces are made up of some kind of excitations which you can represent like being particles. And here locality implies that fields can all interact directly at the same point in space-time. Now, given that we have string theory where we have strings and not particles, that means that some of the problems about infinities which exist in quantum field theory, they do not exist here. Now, in order to have the strings to vibrate and produce, let us call it good music, they have to live in higher dimensions. There were some discussions about that yesterday, okay? Now, we know that we live in 3+1 dimensions, so somehow you have to wind up these extra dimensions, okay? And there are many different ways that you can compact these extra dimensions, and these extra dimensions have to be extremely small, have to be smaller than 1,000th of the size of the proton, otherwise we could have seen them at their limits. So the question is, how many ways you have to get rid or to compactify these extra dimensions? And then the answer is that you have exponentially many ways of doing that, and this is the issue of the landscape of string compactification. So, in addition, if you want, when you go to the down to the 4 dimensions, to have a supersymmetry, then you have about 100 of 1,000 kind of moduli fields. So this is the problem of moduli stabilization. So if you have even only one compact such dimension, then you have something like 10 to a power law, which is the number of the moduli fields which you have, that you can have the possible number of the vacua of the compactification scale. So this is the problem. This is a landscape problem that has been discussed before. And of course, now is the issue of these initial conditions that yesterday has been highlighted, whether we should consider it like something we have to explain or not. And of course, on the other hand, there are people from string theory who might argue that indeed, if you have some complicated physical theory, in order to be able to explain the physical work on which we live, then it might very well be that you have a landscape of possible solutions. And yesterday that was highlighted about the case of GR, so it's something not unique what you see here. But that's something that, look. So based on that, there have been proposed various models of inflation, which they could be, here these things, they could be like brains, that they are embedded in a bulk of dimensionality depending on the string theory which you want to consider. So various models of inflation have been built with plus and positive kind of aspects which they could have. Now let me say a couple of things. Basically, I tell you a bit of each of these theories and the negative aspects more than anything that you might have. For me, the landscape is not a positive thing. So in the case of loop quantum gravity, so here, space-time, it is made of quantized, discrete kind of loops, which you can express like this one-dimensional objects, this kind of loops. Which means that if you want to split time in smaller and smaller bits, at some point, you cannot anymore because you hit the discreteness of your space-time. And this is the quanta of space, which I guess Daniele also discussed yesterday. Now, there is a basic difference between string theory and this kind of, if you want, loop quantum gravity. In string theory, the gravitational field includes the background of the quantum field. Here, in loop quantum gravity, there is no background of space-time, which means that the loops are indeed the space. So you cannot say what is the location that you have on your net, but what you can say as well of your net, but what is the location on the net, because the space is made out about this from this network of intersecting loops. Now, then this is the wishful theory, which of course we don't have, and then you go and you build some kind of mini superspace approach, and you have a loop quantum cosmology. So here you make a jump. You go from the field theory, it's the same thing in string theory, you don't have the full string theory, okay? You freeze all these moduli fields, you take one and you consider, this is going to play the cosmological role I want. And something similar you can do here. And then there have been models, approaches, loop quantum cosmology, which are loop quantum gravity motivated models, okay? So when you test those, you test the particular kind of cosmological model you have, and you have to wonder whether the results, the predictions, could be applied in the full field. And then in these models, you go and you build, how you can solve the initial singularity, how you can explain the temples of black holes, what can you say about early universe perturbation, and so on and so on. Now, here here there is myself a negative thing which I see, even though by saying that I criticize also myself in the sense that I've been working with this model, so I don't criticize just what other people have been done. So you put the matter content of your theory by hand as a classical thing. So this is something which I don't particularly like. So of course you would expect at some point the matter content to come from this geometrical approach, but has not been done so far. And the second thing is that you test predictions of the theory in the semi-classical limit. But what it is the semi-classical limit? How do you define semi-classical limit? Okay? So there are two questions here. What you have to do, first of all, is to understand the notion of observers in a quantum gravity context, and second one, to construct an effective theory for an observer who can define a regime in which now the geometry does not need to be quantized anymore. So this is the process which you have to do, and it's an open question how this semi-classical limit is defined. And now let me move to the last part, which is non-commutative geometry. Now, so in order to express gravity using the same terminology like quantum mechanics, that means that you have to move from the notion of points to the algebra of coordinate functions. Okay? And quantum mechanics by itself, intrinsically, it is non-commutative. You have no commutativity between the momentum and between the position. So you are going to work with what is called a non-commutative algebra. Now, if you consider a classical space on which you take any type of information which you could have, for instance, phase space, automatically this information cannot be encoded within a quantum approach, which means that some of information it is lost, and this is the fuzziness of your space-time. Now, in this non-commutative approach, which I will more refer to, it is the only kind of quantum gravity, quantum within parentheses, I will say why, where you take in equal footing matter and gravity. So what you consider is a higher, let's say, if you want to call it higher dimensional space, which is more complicated than the extra dimensions of string theory. You have at every point of your four-dimensional continuous manifold an internal zero-dimensionality space which captures the standard model of particle physics, which is the most successful particle physics model we have at hand. Okay? So you have this kind of tensor product for your geometry, which I try to show with this plot. At every point of your space-time, you have an internal space. And then, if you put in this tensor product gravity, you are going to find at the end of the day gravity plus matter on a 3+1 dimensional space. So here there is a different notion of studying geometry. Okay? In other words, geometry, how do we know it? The distance between you and I, so I take, the standard coordinate, the square root of the sum of the squares, blah, blah, the Cartesian coordinate. Here the distance, in other words, the geometry of your space-time is found by listening to the vibration of your space as you bump it. Okay? So from the frequencies of this oscillation, you are going to rediscover what is the geometry of your space-time. And this goes to the question, can one hear the shape of a drum? And now the idea is that somebody bangs a drum next door, we don't see the drum, but we can hear with a perfect ear, which I don't have, the tone of the overtones, and the question is, can we like that make up the geometry of this drum without looking at that? If this you do it in the ordinary Riemannian geometry, then the answer is no. However, if you do it to this tensorial space that I said, that at every point of your smooth, continuous four-dimensional background, you have an internal zero-dimensionality space that captures the standard model of particle physics, then by using a technique which is using a dynamics which is called the spectral action, which sums all the eigenvalues of the frequencies of your space, then it has been shown that you can understand the geometry of this space. And this is called a spinorial drum. Now, by doing that, by following this philosophy, it has been tailored a model that can explain like that the standard model of particle physics. Now here you have a spectral triple, which is defined by choice of the algebra, which if you want is the equivalent of your space. Then you have the self-adjoint operator, which corresponds to a real variable x to the mu. And then you are going to have as well a way of representing the line elements, which is given by a Dirac operator. And if you choose appropriately this algebra, then it has been shown that you can find the standard model of particle physics directly from a geometrical origin. And then, you know, we have built a cosmological model based on that. So one can say that if you take the standard Riemannian geometry and you use Einstein's equations, then you get gravity. If you take this, as I call it, almost commutative space, okay, because I have at each point, this is the minimal extension of a commutative background, and you use the spectral action approach, then you can take you can find the standard model plus gravity. And then, of course, the open question is, if I go to even less commutative space, what can I find? And then you test this kind of model. However, here, there are also questions. It's an almost commutative space. So what, I mean, at the beginning, so in this approach, what you consider is at the beginning there is no geometry, there is no time, and there is a phase transition after which time is the bang, if you want, the time equal to 0, and the geometry, as we know, might exist. So the space at that time should be much less commutative than how I present it here, okay? So how can you generalize this theory? So far what I told you was completely classical. So where is the quantum coming? There's no h bar here. And finally, this and that means that some connection, for instance, with loop quantum gravity could be done there because you have a non-commutativity there as well. And finally, it has been tailored to give you the standard model. So what if I take a bigger algebra? What can I find? Can I find some models beyond the standard model? Could I test this theory at an LHC or so on? So these are the open questions. So my epilogue now, so I arrive at my end. So to my mind, the theory of quantum gravity should at the same token explain the ultraviolet and the infrared kind of problems that we have. Now, which of these theories I gave you the alphabetical order is the correct or any of those? And to my mind, as they stand now, any of them could be right, partially right, or completely wrong, okay? So the only way that we can test these theories is by comparing with nature. Why I'm saying that? Because the first thing might be the consistency of the theory. But this is a mathematical issue. The theory might be consistent, but might have nothing to do with the universe I see. String theory might be a beautiful theory. With all the respect for string theories, I don't criticize, but does it have anything to do with that? I don't know. Let's say something I've been working, group field theory, loop quantum cosmology. Does it have anything to do with the work we live? So this is the question. So, as I said, early universe cosmology, to my mind, I can shed some light about what is the correct kind of way of understanding the fabric of the universe. And one might be tempted to ask questions like, what was before the Big Bang? The birth of our own universe. And in order to do that, one has to come up with a set of variables to describe what should be its constituents, and might not be neither the metric we know, nor the connection. Okay? Now, there is a new language to capture the structure, and might not be the differential geometry we do know and we work with. And then the set of equations to describe its dynamics might not be the standard for general relativity. So of course, we cannot experience the phase of what was before the Big Bang, but this is the beauty of theoretical physics to ask this question. However, we have to keep in mind, as I keep repeating, that when we take a proposal of quantum gravity, which we call it theory, and we go to test it, we make a big jump. So what we test? A simplified version of this theory. And we have to keep in mind how valid are the consequences of that kind of simplified version with a field theory. Okay? So, as I wrote, what we test is quantum gravity inspired models. Okay? So, Historically, the major breakthroughs in physics have been achieved when someone comes up with a theory which is based on a simple premises of universal validity. If you take Newton's with respect to Ptolemy, whatever. Then universality may later be in question, leading to a further development and a new step forward. Example, general relativity. So I think that now I feel that we need to take one more step. So we accumulate more and more data, very precise data, and then, however, we still do not have the most appropriate kind of framework in order to analyze them. So what we do, we play with models and not with theories. And I do believe that science does not get along with many laws like models, and it needs real theories. So certainly there is no doubt that mathematics plays a very important role, and is the appropriate language in order to be able to come up with the theory that is going to formulate in the best possible way the laws and natures of the physics of the universe in which we live. So this is, if you wish, what was said by Wittner long ago, the unreasonable effectiveness of mathematics in natural science. So my question is, do we have the appropriate mathematical tools in order to be able to build the appropriate theory of quantum gravity? And here I have a question, I don't know. And with that, thank you very much.
All right, we got lots of time. We'll go ahead and start here.
Okay. Maybe I would only like to ask you about clarification of the important term which you use, because it is used in different senses, and I'm speaking about non-commutative geometry. I also, in some sense, use it, but mostly people working, mathematicians working in the field of non-commutative geometry, they have in mind that coordinates do not commute. And another possibility, which actually I thought this is my topic, is that coordinates commute, but but the components of space-time mapping does not commute. So, in your version of non-commutative geometry, which quantities do not commute?
The version of non-commutative geometry which I refer to is much simpler than that one. It's just you have, as I said, at every point of your normal, continuous, standard space-time, okay, you have an internal zero-dimensionality space that captures the matter quantity of the field. So this is the type of that's why I call it the enormous commutative space. So as an example is how through this kind of mathematical model, if you wish, I can give a geometric kind of explanation for gravity plus standard model.
Okay.
So what you talk is a non-commutative. I'm sorry.
Another way. Okay.
So it's another way. Yeah. I think there was a question next to Daniel.
Jim is the next one.
Sorry.
Yeah.
So I was a little bit confused by what you meant when you said that the space was zero-dimensional. Can you just say what the internal spaces are?
It's a zero-dimensionality space. It has 0 dimensions. There's no special dimensions. There's no.
What is the space?
There's no space there. So it's a zero-dimensionality space. It's like it's like if you take a point. If you take like a Kaluza-Klein theory, okay, where you're 4-dimensional at every point of your 5 dimensions, you have an internal zero-dimensionality space, 0. I don't have any space there. This is a way to capture the matter content of the theory. I don't know how to explain that. There's no space. It's like a point.
Can you just say what is the mathematical structure that's being described by a zero-dimensional internal space?
What do you mean by the mathematical structure? There, what I choose in this space to have, which is not a space, it's just I put my fermion fields.
different than what we usually do with field theory?
You normally have, you might begin, for instance, with a principal bundle. Your internal space is SU3 across SU2 across U1, which is certainly not zero-dimensional.
Yeah, no, I'm agreeing with you. I don't understand.
Oh.
This is the model. This is the model of Alain Connes. So he took at every point of your space-time an internal, as I said, zero-dimensionality space. Like there's no space there. That's why I say that is the almost commutative. There is no, I mean, space. The standard space is commutative. It's the standard kind of four-dimensional space-time you have. So I cannot give you a kind of geometric interpretation.
How do you have to describe the standard model?
Sorry?
How do you have enough degrees of freedom to describe the standard
This
model?
will come with the choice of the algebra which you are going to make. I can give you details. The choice of your algebra, okay, is going to give you, that's why it has been tailored by the choice of the algebra to get the standard model. The distance, it is measured, it is given by the Dirac operator, which I gave there. Okay? So this is just, you just select there to represent all the matter content of the standard model. That's why I say it is a model that has been tailored to give you the standard model. I can give you, if you want, but it's not going to help, you know, I don't see how you can visualize it like the figure I saw there, that, you know, at every point I had this sphere, now this sphere is a point. There's no space.
So how could like 2 points in the 4D space be different with respect to this extra 0 dimension?
But the distance, you wouldn't see the distance, you wouldn't think of the distance the way that you see distances. So the distance, as I said here, the geometry, it is given by this kind of spectral action approach, which you have the sum of the eigenvalues of your Dirac operator. And that is going to give you the modes of vibration of your system, and therefore you measure the distances. You measure the geometry and then the distances, which is not given, so you should not think of the standard way that we see the...
Do you want to follow up, Nick? We have a finger from Tushar.
Yeah, sorry. Just a quick finger on that. So with the spectral triples,
Yeah.
you have an algebra which in this case is non-commutative. So that's one way in which you're talking about this as being a non-commutative theory. And then you've got the fermion propagator, out of which you build the equivalent of a line element, which you then use, which generalizes the notion of a distance. So that I sort of understand. Then there's the other way of describing non-commutative field theories, where non-commutative geometry.
It's not a field theory. This what I discussed is not a field theory.
Sorry, that was a slip of the tongue. Yeah. Non-commutative geometry, in which you take the particular spatial coordinates.
So you talk about the Moyer plane and things like that.
Yes.
There is nothing to do with that.
So
I don't. So this Moyer plane, you know. So you have this has nothing to do with what I discussed.
Okay. So then my follow-up question is, in terms of the spectral triple, there, where does this? How does that translate to this picture that you've given of a Riemannian 4 geometry with the extra structure of a point at each
This
point?
will give in the spectral triple, as I told you. So it's how do I characterize? So I need 3 things in order to characterize this approach. So the algebra, the Hilbert space, and the Dirac operator. So the algebra is chosen, the Dirac operator will give you the distances. So now if you want to see what are the dynamics of the space, you take the corresponding of Fourier space of commutative space, and the corresponding of the Fourier is this spectral action approach, which gives you, I say, the eigenvalues of your Dirac operator. So the dynamics are given by that approach, which is the generalization of the Fourier analysis for non-commutative spaces.
All right. I don't want to take up much more time, so I'll...
Chris.
Yeah, I had just a very specific question about the point where you made what you said was a self-critical point about loop quantum gravity, where you said it was a flaw that you had to put the matter content in by hand. And I was curious why you saw that as a flaw, because if you just thought of loop quantum gravity as quantizing the gravitational field, it's not clear why you'd expect the matter content to come in from that.
What I was saying, I referred to, I'll tell you the example. So we have been studying inflation in this context. So you take the modified Friedman equation, which comes from loop quantum cosmology, and you put the matter Hamiltonian by hand, as you do standard GR. And this, for me, is a flaw.
So you'd expect, but the question is, why would you expect the matter content to be determined just by quantizing the gravitational field?
It should come from the, so I would like to treat matter and space at equal footing, which is not. Because I modify one according to a theory, and the other one I take it from standard particle physics. And also in the sense that I would expect that if I have a different kind of geometry, for instance, the evolution of the universe will be dominated by this different geometry, not through an extra matter field, which for me captures what I don't know geometrically how to explain it. For instance, I would expect, and this we did it in group field cosmology, how inflation can come from the dynamics and the way of gluing this kind of quanta of space which you have. Something along the lines of the Starobinsky inflation, if you want. I would expect that given the energy at which inflation took place, it should be a quantum gravity effect. Also given that we do not know of any matter field people playing with Higgs inflation, but you need some kind of fine-tunings for the coupling in order to get it. Right. So that's my criticism, that I built a cosmological model where half is standard cosmology and half...
So that's a very specific, then, criticism related to inflation, but I thought it was also, there's a more general question, do you expect to get all the standard model fields out of quantizing geometry, or for those, do you think you'd have to have some other input?
I would, for me, a theory of quantum gravity should explain me the geometry plus the matter content. And I don't think that this non-perturbative approach to quantum gravity had achieved that. That goes to the question, to the discussion yesterday, what do you put as an input? So at some point, if, as I think your colleague said, if you are convinced that this is the theory, then you might accept some kind of input. So the way that I see is the following, that what we try to do, we try to build a model in order to understand the universe. This model might not be unique. At the end of the day, who are we that we are going to find the way? Okay? A model. So now, this model, in order to work and be consistent with everything, it might need some input. The input can be values of constants, can be initial conditions. So that's what you put, the threshold. So I would prefer that I had more general view, but.
So we have.
Yes. Hello, this is Ding here. My question is about the non-commutative geometry model. You said it's Riemannian geometry. Do you mean Euclidean signature?
No, unfortunately, no. You have the standard problem here, like in every kind of approach between Lorentz and Euclidean. It is Euclidean.
It is Euclidean, so it's not a big problem. I mean.
Depends whom you ask if it's a big problem or not. There are attempts to treat this problem. I don't think that there has been a lot of effort, but yeah.
So you said there's some cosmological model.
Yeah,
coming from it. I wonder, like, how is it the cosmological model for Euclidean geometry?
No, you assume that somehow you went to Lorentzian geometry without knowing how. But this is the standard thing that has been done in all the non-perturbative approach to quantum gravity. You have the same thing. So I agree with you that is a problem, but it's not the only one. There are others more important to my mind. But anyway, so what people are going to argue is that is a technical thing in order to go from Euclidean to Lorentzian. Some attempts have been done. The community is very small, and this has not been achieved yet. So we expect that somehow, this switch has been made with no consequences, but it's a grain of salt you have to take. So the model, if you want to know, so what this model gives you cosmologically, if you wish, as the Lagrangian which you have, is higher order derivatives. You see, so that's the standard kind. So you get like a way to motivate a kind of modified gravity with R² kind of terms.
Mike?
So, I'm fairly certain this is a clarificatory question. so I'm thinking in the almost commutative
Yeah.
geometry, so you have the four-dimensional space where you associate at each point
Yeah.
the algebra that gets you standard model. What is the connection, or how do I understand the results or the parts of QFT in cosmology that depend on QFT in curved spacetime, or the global?
You don't expect
symmetry
anything
of-
to be changed. So let me try to say in one sentence, so not people think that this is more profound than what it is. The whole approach was to build a geometrical way which can model geometry with a standard model. Nothing more profound than that. So now, okay, so you take the geometry as we know it, of the continuous four-dimensional Riemannian geometry. You have this internal space where you select an algebra to describe it so that you have the standard model. So at the end of the day, you tailored a mathematical model to account for gravity and standard model. Not more profound than that. Then of course the important question is, where on earth this model comes from? How can I start from a fully non-commutative space, so I don't forget, and how I can go to that? I put a plot at some point, a figure, and said with some question marks, we don't know. So this is the lowest kind of extension of a commutative, fully commutative space. But of course, how you come there, that's then an open question. I don't know, nobody has done it.
So is it?
And let me make a comment on that, which, well, everything is recorded, so it's not politically correct, but I'm not known for being politically correct, so I'll tell you that. So now people in that community have spent a lot of effort trying to tune everything, so you get the correct mass of the top quark, the correct mass of the Higgs, and so on and so forth. And to my mind, these are details. What the community should have done is take a bigger algebra, try to make this step, which of course probably is much more difficult to do. So you think all of these kind of details, but this construction you have to see how So don't try to make it more complicated. It's not the non-commutative field theory approach that then Alexei said before. No.
So first, one comment regarding the discussion of whether quantum gravity should determine the matter content. Just my viewpoint is that this expectation that quantum gravity should be a theory of everything maybe is over ambitious, and history has shown that. The classical level, GR doesn't determine at all the matter content, and we are very happy to have GR. You tell me what matter is in the universe, I will tell you, GR tells me how matter and geometry interact with each other and evolve in tandem. And I am extremely happy with GR. So if in quantum gravity I get something similar, I am able to quantize the gravitational degrees of freedom, and if you give me a matter content that theory describes in tandem how this system evolves, I'll be more than happy. So that's my viewpoint. And my question is...
Can I comment on that?
Please.
I agree with you that this is a kind... I agree that this is a kind of where do you draw the line? I mean, what do you want the theory to explain? However, I think that to have the theory of quantum gravity, the interaction between, gravity and the matter field should somehow come into that game. So I feel a bit uneasy when you take a more full theory for one, but the other constituent, which is the matter field, you just take, So I would be happier if I could find a theory that can put under the same umbrella both constituents, but I agree with you that if we have a full theory that could explain everything else and all that, we could be happy, but we're not there yet either, no?
So my question is, you described these three approaches to quantum gravity, string theory, loop quantum gravity, and non-commutative geometry. So could you discuss or tell us your viewpoint about whether these three entities are incompatible with each other, or you think there is a place where they can complement one to the other?
Yeah, I think that, for instance, this spectral action, this non-commutative approach, it could be connected with loop quantum gravity, because there is also there non-commutativity, and then one could try, and there has been some attempt, but it's very difficult to make the link, to be able to use Azteca variables in order to express this kind of spectral action, and it was quite inconclusive how this you could do it. Now, I think that there is a basic difference in the sense that non-commutative approach is a bottom-up approach, and the other ones are top-down. In the sense that in this non-commutative approach I described, is you don't start with how the theory should be at the very high energy scales, but you take what you know at the kind of electroweak scale where your LHC experiment works, and from there you try to go up. So there is, so where they could meet these theories, I don't really know. It's hard to find the connection between the string theory and LQG and all these stacks, because one is perturbative, the other is a non-perturbative approach. I don't know how you could link them. Now, if you want to ask me whether I support any of these theories, I'm completely, from my point of view, I want to test these theories, and I do cosmology as far as I can. As far as I'm concerned, any of them could be right or completely wrong. So I don't have any prejudice, and I will not sell one more than the other. So I discuss more the last one just because it has not been covered before, not because myself I believe that this is the correct approach. So, but there is no way to find out unless, as you know very well, we play with them.
Daniel. This Daniel, then Daniela.
First of all, I apologize. I'm going to ask a question even though I arrived late. So I missed part of your talk. But I wanted to ask if in the non-commutative approach, once I go to the Lorentzian regime, do you expect drastic violations of Lorentz invariance, given that there is no, antisymmetric Lorentz invariant tensor?
I don't know. But the theory, what we use in this theory finally, when we make this, we take the sum of the eigenvalues of the Dirac operator, we truncate somewhere. So you might as well think that when you have the complete theory, these things could be cured. So I don't know. That's not something that has been...
But it's hope that somehow effectively it will be cured, even though at the fundamental level you have that feature.
Yes. But has not been worked out. It's one of the among the list of the criticism that within the community that people have that has not been more.
Daniel.
Just one further comment on the issue of matter and geometry, and whether we should try to extract matter from geometry or from quantum gravity together with space-time. I think I agree with what you said, that it's not needed in principle, and in fact you can proceed without even attempting to do that without any trouble. If what you're trying is to quantize geometry, as it is in the usual approach in quantum gravity and in other contexts. But I also want to point out that our definition of what matter is relies on the notion of geometry in space-time. So we define matter fields as representations of the Poincare group in flat space, or at least locally how they transform with respect to the Lorentz group in a more general geometry. So we rely on a lot of geometric and space-time notions. So what we just said, and what I agreed with, will immediately not be true the moment we start using degrees of freedom or structures which are not directly standard space-time ones. Because in the same sense in which space-time and geometry as we know them, with all their ingredients, will have to somehow emerge, be reconstructed from something else, matter will only appear as we know it through the same reconstruction process. So the moment we modify the fundamental structures, we are going to find at that more fundamental level there will be some counterpart of usual matter fields, but not the usual matter fields. And many of the properties, including the type of matter fields that exist, that will have to be explained and re-derived in the same process by which we make space-time emergent. Moreover, if there are new types of degrees of freedom, even though they may be close to geometry or geometric fields, we may well expect that there will be features of those more fundamental degrees of freedom that after the emergence of space-time has taken place, in a sense, will now look like matter-like degrees of freedom or additional degrees of freedom on top of the usual ones. In this sense, this point also connects to the other question you raised about the possible relation between quantum gravity and string theory, for example. The moment you are in a picture in which space-time in some sense may be limited, not really radical, emerges, there will be possibly new degrees of freedom that in the emergence process will look like a weirder type of excitations on top of the usual space-time, for example, string-like excitations. So one can envisage, at least as a matter of principle, a number of possible mechanisms, both for explaining some features of matter fields, on the one hand, and in connecting to other approaches like string theory.
Did you want to respond or comment on that?
No, I don't know. I mean, I don't have a comment. It's a kind of point of view that, you know.
Okay. Daniel has a finger. We'll do Daniel, Karen, and then we have to be done.
Okay, this is a comment on my almost Daniel Scott. I agree with everything he said, except that I think there is a point that needs to be emphasized. There's a point that needs to be emphasized that is not often done. In various approaches to quantizing gravity, ignoring the matter sector, one is careful to introduce the mathematical structure and then identify objects that we give them the right names, areas, volumes, and so forth. And then we presumably recover something, we call it geometry. But for it to really be the physical geometry, it's imperative that matter reacts to this geometry in the appropriate way. It doesn't serve any purpose if I obtain some geometry and I'm not able to account for the way, let's say, in the classical limit, matter will follow the geodesics of that geometry or something of that sort. So without putting matter and showing that the matter reacts to the things that you have given geometrical names in a proper way, you have not really recovered space-time. You have recovered something that you have given the names of space-time, but it has to have, played a role in the physical world that we know it plays.
Yeah, I agree with what you said, because that's what I tried to say also a couple of times before, that in order to have a theory of quantum gravity, you need to take into account the interaction that gravity has with matter. So I said that in my talk, I said that before, so that's a very important thing, otherwise, you have one part of the game, and it goes to the statement that I made, that you might have a beautiful theory that might have nothing to do with the place, the nature in which we live. So interactions between the matter and gravity is important. That's why I keep finding as, let's say, negative if my theory can tell me nothing about the matter content and you just put by hand what I know.
All right, quick question from Karen.
Is there enough time?
According to my clock, we have 4 minutes.
Yeah, so you mentioned, asking how we can test the theory of quantum gravity, and you said self-consistency isn't enough, we need to compare it with nature. But then you finished by talking about the maths, and do we have the right maths to do it? So do you think the mathematics is the way of making the connection with nature?
No, the mathematics are needed in order to have the correct tools in order to describe a fundamental theory. That's why I keep saying that I'm not sure whether the tools that we have today, which were appropriate for GR, are appropriate for this full picker theory which we tried to build. Now, once we have that, then the next thing is to be able to compare it with data. But the drawback there, I have nothing better to propose, but we have to keep that in mind, that how many assumptions and how important are these assumptions when we take a theory and we go to a kind of simplified model, because only the simplified model we can test. And this is valid for all theories that we said, and I highlighted in 3 of them. So the mathematics are needed for the formulation of the full theory. So we might not have them. That's why it's the difficulty to have the full theory. Because mathematics, as well know, they go independently of physics or along with physics. Some things have been developed for physics, some things have been driven independently, and then we took them in the community as physicists and we use them. So probably we don't have them yet for the full theory. But then you have to test with the data. But the data goes, first of all, to the simplified model, and the second one, that the raw data are useless unless you put them in a context, and then you find the consistency check. So all these things have to be taken into account and not, forgotten. That's what I wanted to say.
Okay, if we have more questions, we could talk to her during the break. Let's take her.